Today's lesson is on average rate of change. This is going to be a very important concept for you, especially if you're moving on to calculus. Calculus really just studies change. In the past, you have studied change by looking at slopes of lines. We are going to look at change, the rate of change, in a little different way. So let's start off by answering these questions. What is average rate of change of a function? So think about what you know and what that brings to mind and what we just talked about. Well, the average rate of change of a function is really just slope. So we're going to be looking at slope. Let's review then. How do we calculate slope, or in other words, average rate of change? Well, again, if you remember back, it's always going to be the change of y over the change of x. But we're going to spell that out. So the change of y is really y2 minus y1 over x2 minus x1. That's our rate of change. That's how we calculate slope. Let's look at this third question. What does a secant line look like in a nonlinear function? So we're going to be dealing with these nonlinear functions and looking at average rate of change. Well, how do we do that? We do that by looking at secant lines. So let's go ahead and first look at a tangent line. Remember that a tangent line is called a tangent line because it touches something, say for example a circle or a curved part in exactly one place. So if I were to draw a tangent line here, for example, we would want to know the average rate of change here at this point. Well, we know what this point is. It's about 1.1, comma, maybe 0.4 or 0.5. But that's not enough information, right, to help us find our slope or our actual rate of change. So instead of using a tangent line, which will find us the instantaneous rate of change at any point on this nonlinear function, we can use a secant line. Let me draw one here. And a secant line is called a secant line because it actually connects 2 points on the graph, which is what we need in order to find the equation of a line, 2 points. So in this case, I could say, well, I know my point here, and I know my point here. If I find the slope of this secant line, it's going to be very close to the slope of the tangent line. And if I continue to travel down this nonlinear function, eventually I'm going to find the slope of this tangent line, which we call the instantaneous rate of change at this point. So what we're going to be working on today is just finding the slope of a secant line. This is also going to be important in your future study of limits with calculus. All right, let's try a first example. In this example, we have the function y equals 2x, or f of x equals 2x. This is a linear function, so it's pretty straightforward. It's going to be easy to find the average rate of change between 1 and 3. Now, what is 1 and 3? These are our x values. We're always talking about our domain when we're trying to find the change between values. So always consider these to be our x values. Think about what's missing. We don't have our y values, but we can find those y values. So let's take our first point because we need 2 points. For our first point, we know that x is 1. All we have to do is plug it in order to get y. 2 times 1 is 2. That's y. Now we can look at our second point. For our second point, we have the value 3, and when we plug that in, we get 6. Now that we have our 2 points, it's really easy to calculate our average rate of change. So our average rate of change is going to be y2 minus y1 over x2 minus x1. And that will give us 4 over 2, or 2. So our average rate of change, and you can see that right in front of the x, the slope is 2, and we proved that. So between any points here, we're going to get the same slope because this is a linear function. But what happens if we have a function that's not linear, like the one we looked at before? Here in blue, we have the function x squared. That's not linear. How can we find the slope of that function? Well, we can start by finding the average rate of change. So let's first find the average rate of change between these 2 points, 1 right here and 2 right here. And I've drawn that in with a red line. So you can see that if we find the slope of this red line, it's going to be somewhat close to the slope of this blue line. So let's go ahead and do that. So let's find our 2 points. For our first point, if we plug a 1 in here, 1 squared is just 1. For our second point, if we plug a 2 in for x, 2 squared is going to give us 4. So if we want to find the average rate of change for the distance between 1 and 2, we can take y2 minus y1 over x2 minus x1 to give us 3 over 1, or just 3. So the slope of this red line is 3. Let's compare it to the slope of this green line. This is also a secant line to our nonlinear function. So let's find our first and second points. For our first point, if we plug a 1 into our function, we still get 1. However, if we plug a 4 into our function, 4 squared is 16. So now if we're finding our average rate of change for this secant line, we're going to get y2 minus y1 over x2 minus x1. That gives us 15 over 3, or 5. Very different. So if we continue to move our line, our points, closer and closer to this point here at 1, 1, we will eventually find out the instantaneous rate of change of this point. It's kind of like I said before, it's like a limit. As you get closer and closer and closer, what's going to be our value? So let's give ourselves a generic equation in order to help us. Let's find the average rate of change between 1 and some number x. We already know when we plug in a 1 for our first point, we're going to get a 1 as a result. What happens when we plug in an x? Well, if we plug in an x, we still get x squared. Now let's go ahead and create our generic equation that we can use. So we have y2, which is x squared, minus y1, which is 1, over x2, which is just x, over x1, which is also 1. Let's simplify this a little bit because this is difficult to work with. So look at x squared minus 1. Hopefully you remember that that's a difference of squares. X squared is a perfect square, and so is 1. We can factor that into x minus 1 and x plus 1. And that's all over x minus 1. Now let's go ahead and simplify. X minus 1 and x minus 1, those cancel, and we're left with a generic equation of x plus 1. Let's test it to make sure that's correct. Well, what if we want to find the rate of change between 1 and 2? Well, this is the rate of change between 1 and any number x. So if we plug 2 in here, 2 plus 1 is 3, that's what we got. Let's try the second one. The average rate of change between 1 and 4, if we plug 4 in here, 4 plus 1 is 5, and that is in fact what we got. So this generic equation can help us find the rate of change between any 2 points from 1 up. So if we wanted to find the rate of change, for example, between 1 and 1.1, we could put a 1.1 in here and get 2.1. And you can see how we could continue to put in smaller and smaller values, or closer and closer to 1, in order to figure out really what that rate of change is right there at 1, that instantaneous rate of change, which would be on the tangent line. Let's try one more example before we go. Let's find the average rate of change of this function. It's a little more complex. So let's go ahead and start with our generic equation because we know that can help us. So let's find our first and second points. Pause the video and see if you can do that. If we look at our first point, if we plug a 1 into this equation, we get 2 times 1, which is 2, minus 3 times 1, which is just 3. So 2 minus 3 gives us a negative 1. The x, that's going to be a little more tricky. If we replace all of our x's with x, well, we end up with our same equation, 2x squared minus 3x. So now we have our y1, y2, as well as our x1 and x2. Let's go ahead and make an equation and simplify. Here I have my y2, 2x squared minus 3x, and then minus a negative 1. In other words, plus 1. Minus a negative 1 is the same as plus 1. And then we have our x2, which is x, minus our x1, which is just 1. We need to factor this top quadratic, so think about how you might factor this. We need two factors, and we can take our 2x squared and split that up into 2x and x. You can also factor this by grouping. If you need help with that, I can give you an additional resource if you let me know. I went ahead and put in a minus 1 and a minus 1 here because I know I've got a 1 on the end, and the only thing that you can multiply and get 1 is 1 and 1. In order to have a positive 1, these either need to be both positives or both negatives. Since my middle term is negative, I find that these need to be both negatives. You can always factor and test it out and make sure that that is what the quadratic factors into. All right, we'll put that over x minus 1, and then we will simplify, which leaves us with our generic equation of just 2x minus 1. Using that, I can now find the average rate of change between 1 and 8 by merely just plugging in an 8 into x. So let's do that. The average rate of change from 1 to 8 is going to be equal to 2 times 8 minus 1. 16 minus 1 is 15. And now I've calculated the average rate of change between 1 and 8 in this nonlinear function. And that concludes our lesson on average rate of change. So think about your goal. Think about what you're trying to do. Ultimately, eventually, you will be finding the instantaneous rate of change of a point on a nonlinear function that is connected to a tangent line. Right now, we are just going to find the slope of a secant line between a starting point, 1, and any point along the secant line, x.